This is General Physics 2, nope, 1, and we're doing chapter 12 problems. First problem we're going to look at is number 3. It wants us to calculate the wavelength of light, wavelength of the sound wave at 20 hertz and at 20 kHz and at 18 megahertz. And from the book we know that frequency is equal to velocity times wavelength. If I can make a wavelength. So now the only issue is knowing the velocity of sound at 20 degrees. And I'm thinking it's 343 meters per second, and I would be right. 343 meters per second. So the wavelength is going to be the frequency divided by the velocity. So 20 hertz divided by 343, and 220 kHz divided by 343, and 18 megahertz divided by 343 meters per second, and we end up with an answer in meters. So we go and let's reconsider this for a moment. The formula we want is velocity is frequency times wavelength. And so wavelength would be velocity divided by the frequency. So that makes every single thing I've written so far wrong. Luckily I have a big enough eraser. Reconsidering is always okay. Let's see, so 343 divided by 20 hertz meters per second, or 343 divided by 20K, or 343 meters per second divided by 18 meg. All right, now we're ready to use our calculator. 17 point, well, just 17, I guess. 17 meters. Um, 17 millimeters. And 19 micrometers. Doesn't look like a micro, so we'll go back and do it again. 19 micrometers. Okay, so that's all there is to 3. Looking at number 6. A person with his ear to the ground sees a huge stone strike the concrete pavement. A moment later, 2 sounds are heard from the impact. One travels in the air, the other through the concrete. They are 0.8 seconds apart. How far away did the impact occur? Okay, so distance is velocity times time. Okay, So here I am sitting there, I'm the person, and I'm listening. That's my ear to the ground. And so I have some velocity through the concrete, some velocity through the air. Okay, through the air I'm going to be at 343 meters per second. What is the velocity of sound through concrete? And we look at page 329, and we see that it's about 3,000 meters per second. So I said, well, 3,000 times t is going to be equal to 343 t plus 0.8. So it takes 0.8 longer to go the other way. So now the only thing we have to do is figure out what t was. Once I find out what t is, then I can multiply it by my speeds and come out with what the distance is. Okay, so I've got 1, 2. I got 2, 6, 5, 7. T is equal to 0.8. T is equal to 0.8 divided by 2,657. All right. 0.8 divided by 2,657. 310 microseconds. All right. So 0.8003 times 343 means that I'm 274.5 meters away would be my distance. And then I go back and see, well, I only have 2 significant digits, so I'd say 270 meters would be my 2 significant digit answer. Okay, now we're looking at problem number 6. No, we just did problem number 6. So we're going to go to problem number 13. A CD player has a signal to noise ratio of 82 dB, whereas a second CD player has a signal noise ratio of 98 dB. What is the ratio of intensities of the signals in the background for each device? Alright, so 82 dB is 10 log intensity of the signal divided by the intensity of the noise. Okay, and so we're going to go and divide by 10. 8.2 is log intensity of the noise, and they're going to raise these as powers of 10. So what we're looking for is the intensity of the signal and the intensity of the noise, that ratio. Alright, so turn on a calculator. 10 raised to the 8.2. And it's going to be 158 1.6 times 10 to the 8th. And then we're going to do it again. Intensity of the signal to the noise. And that's going to be 10 to the 9.8. So 10 to the 9.8. 6.9 times 10 to the 9th. And number 15. A rock concert registers 130 dB when you're 2.5 meters in front of a loudspeaker on the stage. Right, so we got us. There's our stage. There's our loudspeaker, and our distance is 2.5 meters. What is the output power of the speaker, assuming uniform spherical spreading of the sound and neglecting absorption in the air? How far away would you have to be 85 dB? Okay, so the first thing we have to do is look in the back of the book to find the area of the surface, of the surface of the sphere. And we find that that's 4 pi r squared. 4 pi r squared. All right. And then we're going to have to do and figure out what that is at 2.5 meters. So the area of a sphere at 2.5 meters is going to be 4 pi 2.5 squared. 4 times pi times 2.5 squared. 78.5 meters squared. No, that doesn't seem too big. Okay, so that being the case, now 130 dB means 10 log intensity divided by intensity naught. And our intensity naught is 10 to the minus 16th watts. Alright, so now we have 10 to the 13th is equal to intensity divided by 10 to the minus 16 watts, implying that the intensity is 10 to the minus 3 watts. Okay, and the intensity per meter squared okay, so that's the intensity, that 10 to the minus 3 watts. And that's going to be at 2.5 meters. So I'm going to take that. And this would be watts per meter is what it would be in. So I'd have to take it and go 10 to the minus 3 times 78.5 meters and end up with 0.78 watts. Now we know that that's not right. So what is it that I am doing wrong? This is 15. 15's in 10.2. intensity naught. Oh, it's 10 to the minus 12th. That's right. That's what I'm doing wrong. Intensity naught, which is 10 to the minus 12th watts per meter squared. Okay, so that being the case, my intensity is going to be 10 watts per meter squared, and the wattage of my amp is going to be 10 watts per meter squared times 78.5 meters squared. So I'm going to have a 785 watt amplifier. Now the issue is, that's the A answer. So now we're going for the B answer. How far do I have to be away to only have 85 dB? Okay, so 85 dB is going to be 10 log, whatever my intensity, 10 to the minus 12 watts per meter squared. All right, so I'm going to divide by 10, 8.5 log I 10 to the minus 12, and I'm going to raise both as powers of 10. 10 to the 8.5 times 10 to the minus 12 is equal to my intensity, which is going to be 10 to the minus 3.5. Okay, so 10 raised to the minus 3.5 is 0.000316 watts per meter. Okay, so I want 0.000316 watts per meter squared. That's really meter squared. All right, now that's going to have to equal all right, so 785 watts is my speaker. I'm going to have to divide that by my spherical spreading, 4 pi r squared. And I have to solve for r. Okay. So I've got r is going to equal square root of 785 divided by 4 pi 0.000316. And I think all those units are in meters when I get done, so that'll be good. Square root of 785 divided by 4 divided by pi divided by 0.000316, and I end up with 444 feet. And how many significant digits do you think we have? We only have 2, so we'll call it 440 meters. Okay, looking at number 40. A pipe in air at 23 degrees centigrade is designed to produce 2 consecutive tones, 80 hertz, 280 hertz, and 320 hertz. How long must the pipe be, and is it open or is it closed? All right, well, first of all, what is the fundamental frequency? The fundamental frequency happens to be 40 hertz. We know that because these are two consecutive tonals, and in order to be consecutive, they're only different by that. All right, so that being the case, this guy is the 7th, and this guy is the 8th overtone. Okay, so we know that that's the case. All right, now that we got that, we're going to move back to 14.4. And we're looking at page 4338 of 4339. And we see that if I'm going to have a 7th and an 8th guy, my pipe can't be closed because I only have a fundamental, a 3rd, and a 5th harmonic. So that means the pipe has to be open. Otherwise, I wouldn't be, I would only be getting the odd harmonics. And so what are we supposed to be calculating? The length of the pipe. Okay, so the length of the pipe is going to be 1/2 the wavelength. Okay, so the length of the pipe, 1/2 the wavelength of the fundamental. Now, in order to know that, we'd have to know the frequency at 23, the velocity at 23 hertz. And do we know that? We know it at 20 hertz, it's 434, but what is it at 23 hertz? Okay, so looking back on page 329, we find that the velocity is about 331 plus 0.6 t meters per second. And t is in Celsius. So my velocity, 331 plus 0.6 times 23 degrees Celsius. 331 plus 0.6 times 23, 344.8 meters per second. So the length of the pipe is going to be 1/2 lambda, and lambda is the lambda, let's see, the speed is lambda f. So lambda is going to be the speed, 344.8 divided by the frequency, 40 hertz, because we're doing this at the fundamental. So it's going to be 4.31 meters for the length of the pipe. And then we'd ask ourselves, do we have 3 significant digits? Well, we might. So we would keep all 3 of them. Okay, that's 40. Number 53 is next. 53, 2 loudspeakers. Loudspeaker 1, loudspeaker 2, 1.6 meters apart. A person stands 3 meters from 1. Okay, so I'm standing this way, and I'm 3 meters, and then that way is 3.5 meters. What is the lowest frequency at which destructive interference will occur at this point if the speakers are in phase? All right. So the lowest frequency. All right. So this one would have to go some number of cycles, and this one would have to go that number of cycles and a half cycle more. Okay, so 0.5 meters is going to be the wavelength, but it's going to be half the wavelength. And so frequency, V is equal to F lambda. So frequency is velocity divided by lambda, and we'll go 343, maybe, I don't know, 55. Doesn't say, oh, assume 70 degrees. Okay, that's good. So we got the right speed of velocity of sound divided by 1. So 343 hertz would be the lowest frequency for destructive interference. Okay, the second part of the question, calculate 2 other frequencies that also result in destructive interference. All right. So I got 2 cycles, and this is 2.5. I have 3. Well, we could do it that way. Okay, so this was 1 cycle. This was 3 cycles, and that was 3.5. So that did it. This could be 6. This could be twice the frequency, and I would still be destructive. So at twice the frequency and 4 times the frequency would be the other 2 answers. So the B part would be 2 times 343 and 4 times 243. Bye-bye. 686 hertz. 972 hertz. Okay, that leaves problem number 58. Two automobiles are equipped with the same horn. When one is at rest and the other one is moving towards the first. Okay, so here's an automobile at rest. The other automobile is moving that way at 18 meters per second. The driver at rest hears 4.5 hertz in beats. What is the frequency of the horn, assuming temperature is 20 degrees centigrade? So that means my velocity is 343 meters per second. And this is 12.7. Now, the beats. Okay, so this guy's going 343 meters per second. This guy, because there's 4.5, well, We don't know. Do we know the frequency of this horn? 58. Yes. No, we don't. Uh-huh. We're trying to figure it out. Okay. So what we need to do is find out the frequency source moving towards a stationary observer, equation 12-2a. Okay. All right, so f prime is equal to f divided by 1 minus velocity of the source divided by velocity of sound, 3, 4, 3. Okay, so we have that one equation. And the velocity of the source is going to be 18. Okay, so that's 18 meters per second divided by that. Okay, f prime is equal to 1 minus 18 divided by 343 equals, and we'll do a 1 divided by my answer. Okay, so we got 1.05538 F. Now, F minus F prime minus F is going to be my beat of 4.5 hertz. Okay, so 4.5 plus F is equal to 1.05538 F. 4.5 is equal to 0.05538 F. F is equal to 4.5 divided by 0.05538, and we probably don't need that many significant digits, but that's okay, we have them anyway. 1 minus the answer. Okay, and then we're going to have 4.5 divided by the answer. I don't like this answer. 81 hertz. And say 4.5 divided by 0.05538. Yep, 81 hertz. Yep, I don't see that we did anything wrong, so, but that just seems like a weird low horn. Okay, good enough? File, Control, Alt,